In sac109A number 2, we've got two particles moving in a horizontal plane. One of the particles, particle B, is moving due north at a constant velocity, and the other particle starts out at a position due west of particle B, a distance 6.00 meters to the west, and it's moving in a direction that makes some angle with the northward direction. In fact, we're asked to find this compass heading. And the question is, what is the compass heading that will make it so that particle A and particle B collide? Now, the collision type 2 equation in 2 dimensions actually involves two little equations. One, the x components of the positions of the two objects has got to be the same. So xa is equal to xb, and 2, the y components have to be the same in order for them to be at the exact point in two-dimensional space. So y sub a is going to be equal to y sub b. So the way to go about this is to break up the motion into x and y motion, write down the position of each particle as a function of time, and set those two equations, let's say, set those two sets of coordinates equal to each other, the x coordinates and the y coordinates for the two particles. So to break everything up into x and y motion, we first have to ensure that it's doable. Let's see, over here the B particle, particle B, is moving strictly along the y-axis, where I've defined the y-axis to be northward and the x-axis, the positive x direction, to be eastward. So this one's a piece of cake. It's already broken up into x and y motion. It's got no x motion, and it's moving strictly along the y-axis. Particle A, on the other hand, has got an acceleration that's a combination of x and y motion, so we have to break that up into components. Let's get started with that. We'll copy an xy axis over here and do the vector component diagram for particle A. So put for the acceleration vector of particle A, I'll call that a sub a, and that's the vector sum of a sub a x and a sub a y, where the angle that I've got in here, which is just that compass heading, appears right here. That's the theta. Okay, I can't get values for these because I don't know what theta is, even though I do have a value for a sub a, namely that 22 meters per second squared. But I can still express a sub a x as in terms of this angle. So with respect to this angle, this is the opposite, and this will be the hypotenuse. So I got the sine of the angle is equal to a sub a x over a sub a, or a sub a x, multiply both sides by a sub a, I got a sub a times the sine of the angle. Similarly, a sub a y is being the adjacent to this angle. It turns out to be a sub a times the cosine of theta. Alright, now I think I'm ready to write down the positions of each of these particles as a function of time. I'll start with the x position of particle A. Let's see, it'll be x sub a initial plus its initial velocity times t plus 1/2 a sub a x component. This was the initial velocity x component, and this times t squared. Alright, I didn't have to worry too much about this one because it's just 0. That is, particle A started out at rest. It's got neither an x nor a y component of velocity, and it started out at a minus. X sub AO is a minus, just make a note of that, that's minus 6.00 meters. Draw a little separator in there so you realize I'm dealing with this object over here, and this guy's still 0. So I can't white that out, but I do have an expression for x of a. I'll call it x of a initial, the minus 6 meters, plus 1/2 a sub a x component times t squared. Alright, how about the x position of particle B? X sub B, this is trivial. B's moving strictly along what I've defined to be the y-axis, northward, so x sub B is equal to 0. So we said one of my constant acceleration equations, our collision equations, is that the x components have to be equal to each other. X sub A is going to be equal to x sub B. So I get an equation, x sub A, we said is x sub A 0 plus 1/2 a sub x t squared. So I'll copy that down. That's got to be equal to x sub B, which is just 0 for all time. That gives you the x component of the position of particle B at any time. It's always 0. It's just a constant. This is at a special time. I'll call it t star. So this is true at the collision time. Which I'm calling t star. At the collision time, this equation is true, and I'm going to circle that so I can find it later. And I'll call it equation 1. Alright, let's look at the y motion for a little while. Let's see if we can do the same exact thing for the y motion. So that was our vector component diagram. Oh, I'll tell you what, I'm going to actually back up just a little bit. I'll replace that a sub ax with the a sub a sine theta. We'll get that sine of theta into the problem. Sine theta, and then times t star, all squared, and I'll call that one. That form of the equation. Equation 1. Alright, now let's get to work on that y component business. I'm going to try y sub a. It's got to be equal to, I'll just copy down the same thing, but for the y component of particle A, its initial position, plus its initial velocity times time in the y direction, plus 1/2 a sub y times t squared. Okay, what do we got? Initial position is 0. It starts out on the x-axis, so initial y value is 0. That's convenient. The initial velocity is 0. The entire initial velocity is 0. I didn't have to break that up into components. So this time I'm going to remember to substitute that a sub y in a little bit earlier. I am dealing with particle A, so I need a subscript A right there, and that is a sub A times the cosine of theta t squared. Alright, let's look at particle B. Particle B, I'll go ahead and write the whole thing out, even though it's going to be pretty trivial for the y motion I'm working on. Well, initial position plus VB0 YT plus the 1/2 a sub by t squared. Okay, it's kind of trivial because this particle has no acceleration, so that's 0, and its initial position, it started off at what I define to be the origin, so that's 0 as well. So y sub b is just VB0. This is this quantity right here. Since the thing's moving strictly along the y-axis, this is the same thing as VB0, which, by the way, is the 12.0 meters per second. We might need that later on from right up there. So I'll just call it VBO and say times T. Alright, so we got an expression for each of the y positions at T star. We have the y components have to be equal as well. I think I'll go with the A first. So YA is going to be equal to YB. Alright, so the 1/2 A sub A cosine of theta times T squared has got to be equal to VB0 times T. At that special collision time, that's the T star. And that's got to be the same time as over here. So at what's been going on up until T star, this particle's moving up in that direction. This one's accelerating in this direction. And at T star, they both have to be at a position that I've indicated in the diagram where those two lines cross. And at that position, the x components and the y components for both particles have to be equal, respectively. Okay, this is actually got two solutions. When for the time, if the time is 0, this equation is met. And for the y motion, they did both start out at y is equal to 0, so that's just telling us they both start on the x-axis. So for any other time, let's assume that, consider only times when t star is not 0, we can divide both sides of the equation by t star. We get rid of one of them over here and that one over there. So our equation, we can solve this for t star. I think that's going to be my plan. We're looking for theta. I've got two equations and two unknowns. The two unknowns, the theta, the angle at which this particle is traveling, particle A is traveling, and the collision time t star. So there's the two unknowns. A sub A was given as 22 meters per second squared. The VBO is given over here. The only thing we don't know is the t star and the theta. So two equations, two unknowns. I just have to combine those two equations and solve for the unknowns. So I'm going to solve this one for t star. Solving for t star. We get, okay, I'll multiply both sides by 2. That'll be 2VB0. Then divide both sides by all this stuff, the A sub A cosine of theta. Okay, now what I can do is to substitute that right into equation 1. And what I'll get is x sub A 0 plus 1/2 A sub A sine of theta times 2VB0 over A cosine of theta all squared. This is A sub A, of course. Alright, let's go ahead and we need an equal sign up here. This is equals 0. So equals 0 down here. And I think I'll multiply both sides by A squared times the cosine of theta squared. So I have all squared, and then plus, alright, I got a 2 squared in here, multiplying that 1/2, so that'll be a 2. We've got an A sub A, and I've got the VBO being squared. Now that's got to be equal to 0. Could have canceled this out in the preceding step, but let's get rid of one of those. a sub a's, and I left out a sine of theta here. So let's see if I can squeeze that in. Go ahead and squeeze in that sine of theta equals 0. I think we're all set. So now I'm trying to solve for theta. What I'm going to use is the trig identity. Cosine of theta squared plus the sine of theta squared is equal to 1. So the cosine of theta, which is what I've got here, is 1 minus the sine of theta squared. So substituting that in there, I'll have x sub a 0, a sub a, times 1 minus the sine of theta that's squared plus 2 VBO squared times the sine of theta. That's all equal to 0. Alright, I've got what looks like a quadratic equation in the sine of theta. Let's get it into the form of the quadratic equation. I'll multiply this stuff through. I'm going to write down this first term, the part multiplying the sine of theta. So I got the minus sign, xa0, a sub a, sine of theta squared. And then I'll copy down this term. I want to save this one for last because that's a constant term. So plus 2VB0 squared sine of theta. And then plus this term times 1, so just this quantity right here, XAO times a sub a. That's all got to be equal to 0. So I got a quadratic equation. I can solve for the sine of theta as if that's my variable. You know, here it is squared, here it is to the first power. So sine of theta, don't really need those parentheses. Sine of theta is going to be equal to minus b, which would be this term, plus or minus the square root of b squared, so that'll be 2 VBO squared all squared, minus 4 times a, which would be that minus XAO a sub a, times c, minus 4ac, so there's the c, XAO a sub a, all divided by 2 times my a term, which would be that minus XAO a sub a, period. And then I'm going to take the arc sine of both sides to find out what theta is. So it's the arc sine of all of this stuff. And let's see, I've got a 2 squared, which is a 4 there. Factor that out. Take it outside the square root, and it becomes a 2. I divide that 2 into it, get rid of it. Divide that 2 into it, get rid of it. So I've just got the arc sine of minus VBO squared plus or minus the square root of, got rid of this one, and then that's all got to be squared, so I got VBO to the 4th. Then I said I did cancel out that 4, pulled it out and canceled it, so I got minus a minus, and then XAO times XAO, so that'll be an XAO squared, and then an a sub a squared. and that's all divided by that minus XAO times A sub A. And I think I'll distribute that minus sign, so multiply upstairs and downstairs by -1, and the plus or minus becomes a minus or plus, so it essentially we get the same two answers. So I want to take the arc sine of all this stuff, and at this stage I'm ready to substitute some values in there. So I got the arc sine of VBO was 12 meters per second, and then the A sub A 22 meters per second squared. So I got 12.0 meters per second all squared, then plus or minus the 12.0 meters per second to the fourth onto that radical, plus the minus 6.00 meters that particle A was to the west squared, times the 22.0 meters per second squared acceleration squared, and this is supposed to be all divided by the minus 6.00 meters squared. Nope, just meters. Nothing squared down there, and then times the 22.0 meters per second squared. So taking the arc sine of all that, let's see if it is indeed a unitless quantity. So I have meters squared per second squared up there. This would be meters to the fourth per second to the fourth. Meters squared here times, that'll be meters squared, so meters to the fourth, and the second squared will be seconds to the fourth. So meters squared, meters to the fourth divided by seconds to the fourth upstairs, and then downstairs I've got meters squared divided by seconds squared. Oh, that's what I got up here, because this to the fourth stuff, you've got to take the square root. So I do have meters squared per second squared upstairs, and same thing downstairs. So this is a unitless quantity. I've got two results. One of them turns out to be negative, and that's not consistent with our picture. That is, we need the angle that theta has to be clockwise from the straight ahead direction. We get a minus sign. I think that's going to be too big an angle there. So I'm going to take the one solution, which actually corresponds to the negative sign upstairs. This term turns out to be bigger than that one, so that'll make this whole thing negative, and this is negative. So choosing the minus sign here, I find that the angle is 22.9 degrees. And indeed, this is a compass heading.